It's great to have Professor Rahul Kashyap with us today from IIT Bombay, and he is going to speak to us about binary neutron star post-merger signal modeling, impact of AI ML tools. Yeah, please take it away.
I just want to clarify in the beginning that when we do the numerical simulations in binary star mergers, all the information that we obtain from the different, from a series of timestamp of the basic variables like metric and matter variables, we correlate all of them with cold neutron star properties, which is calculated by mapping these equation state curves to mass radius and tidal uniformity curves. So the in parallel system which can have some mass and spin, and that is those masses are mapped to radius or tidal uniformity, and those are used for correlation. So it's just a correlation. The statements like what is the tidal uniformity of in the post-merger neutron star doesn't make sense because we are doing correlation with some initial parameter after doing the detailed simulation, and we can choose any quantity for our correlation, and this is what we choose because we want to constrain these mass density curves. So having said that, I'll specify three main problems which I see having with great scientific output in terms of analyzing post-merger signal. One is this detecting prompt versus delayed collapse in post-merger signal, where just even detection of existence or non-existence of post-merger signal can give us a lot of information. And on top of that, if we can detect the duration of post-merger signal, when does the black hole forms after the binary star merger, with what time delay is going to be very important. On top of that, it is known that the formation of GRBs, short gamma ray burst, in the post-merger era requires a significant evolution of the accretion disk that forms after the merger and subsequent collapse to black hole. Those are essential ingredient of gamma ray burst along with magnetic field as well. So to understand the post-merger waveform and their subtle variations in amplitude and phase, those are very important, especially instantaneous frequency. That will be a golden information about formation of short gamma ray bursts in binary star merger, and similarly for kilonovae, which are the optical transients of the binary star merger, which also forms which is formed by the ejecta that is emitted during merger and in the post merger, and it is clear through many simulations that it is the post merger which contributes more than 50%, sometimes 60-70% of the ejecta of the kilonovae. So the pre-merger ejecta, which is known as dynamical ejecta, which comes from the tidal disruption of neutron stars, could be a very small part. So that means understanding post-merger evolution and accretion disk evolution will be very important. During all these processes, there is a chance, we don't know for sure that, but there is a possibility that QCD phase transition may lead to different effects in the post-merger signal, and we can detect them. So I'll just hint upon all these three, and then I will hand over to the Swayam, who is undergraduate student here, who has just joined to do something about waveforms. So first thing is difference between prompt and delayed collapse. So after merger, it is possible that during the initial collision itself, these neutron star mergers will collapse and form black hole. In that case, what you will see is a long spiral in the last panel of this figure here, and then it will be joined by the ring down of a small black hole, which will be around 6 kilohertz because they are very small. Currently, we are not envisioning any detector to have a significant uh, detect, sensitivity at 6 kilohertz. So we just focus on the post merger. Uh, and in contrast to this prompt collapse, it is possible that these systems will collapse to black hole within few milliseconds, and those will be different than prompt collapse because there will be slight small amount of post merger signal, And then we have long-lived uh, post-merger signal that is on the leftmost panel. And the upper two rows are representing the maximum density and minimum lapse, which is minimum lapse is the signature of whether black hole has formed or not. So usually if it falls below 0.2, that's the thumb rule, and we say that black hole has formed. So in the leftmost panel, there is no black hole has formed. There is no black hole that has formed within up to that 5 or 10 milliseconds, but the simulation has been stopped around 7 or 8 milliseconds. So first of all, detection of post merger, and then so in this case, just purely detection of post merger or non-detection is going to tell us whether it was prompted or delayed. But how does it help us? So in a work some time ago with our collaborator, we had shown that if you can detect sorry, if you can detect whether a system is prompt or delayed, then you can put constraints on the threshold mass to collapse, and then you can rule out some regions in this plane, which is threshold mass versus maximum mass plane. Again, note that this maximum mass is non-rotating cold neutron stars, and this is what we choose for correlation, but you can choose for many other quantities for correlation, which has been taken in Boswine and other groups. So I'm plotting here GW17 or 17, which is confirmed to be delayed collapse because we saw kilonova from it. But I have plotted two others hypothetical delayed collapse with two different masses. So we see that if your mass is above the point here, just above 3.2, then you can constrain better than existing constraints on the maximum mass. Similarly, if you have prompt collapse, you know for sure that these systems are prompt and you know their masses, then you can constrain this maximum mass upper limit, which is currently 2.9, but you can do better than that provided their masses are below 3.66. Whether this will happen or not, we don't know. But if we can do that, and if there are systems which are prompt collapsing below 3.66, that means we can constrain the maximum mass limits. So this will constrain the upper and lower limit from two sides within very few observations, and that's the thing that is interesting about it. Now, if we move to QCD phase transition, then in one of the work with Aviral Prakash, who is a graduate student at Penn State, with David Adichie, he performed a series of simulations which shows the phase transition or its impact in the post merger. So here are two equational states again, pressure versus density curves of BLH and BLQ. The H is hadronic, Q is with quarks, and both equation states have been used in two different simulations, actually multiple different simulations with different masses, and then their effects have been seen in the post merger signal. Similarly, there is DD2F and DD2F-SF are two with hadronic and phase transition with different types of phase transition equation states. And when we do the simulation and we simulate these NR signals, NR post merger signals, and try to recover it using a post merger model, we obtain something which is on the right hand side. So here the dotted curves are the NR signals, and the shaded region are the 90% credible interval that we obtain using one post merger waveform model. This model is called NRPMW, which has been worked out by Matteo Breschi in the Sebastiano Bernoulli's group. So what we see here is that if you have D2F and D2F-SF, whose peak frequencies in the injected peak frequencies differ by about 150 to 100 hertz, they can be distinguished. So as you can see, the injected is the dotted curve, and they are this much different, and our posterior can hardly recover this post peak frequency, but except that other features of the waveforms are completely washed out in the posterior. And the below plot here is the same posterior in the peak frequency and lambda tilde of the spiraling neutron star. So this posterior is plotted in this space, and along with that, what is plotted is the quasi universal relation that has been obtained through multiple simulations. And it shows that if you have a very strong phase transition which shifts the frequency by a lot, then those posterior along with their 90% error interval could lie beyond this universal relation, and then that will give you the signature that there is a phase transition which violates the universal relation. So I'll now hand over to Swayam, and I will share his slides real quickly. Share. Maybe, yeah, should work. Okay, Swayam, please go ahead. So you can cut this face. And
So, am I audible? I hope so.
Yeah, you're still audible.
yeah,
Okay, so,
this is first slide. Yeah.
okay. Good. So, good afternoon all. I am Swam. I am an undergrad in the Department of Physics in IIT Bombay. I have recently joined Professor Rahul Kashyap, and yeah, this is what I have been doing for the past month. It's not much, so I'll keep it crisp, and yeah, I hope we go ahead. So, for now, I have been given about 20 waveforms with the metadata, and the models which I have implemented for till now are the following: recurrent neural networks and convolution neural networks. The physics-informed neural networks hasn't been implemented fully yet. It's in the ideation phase. I have implemented it on some other uh, physical demonstrations like under damped oscillation just to demonstrate it. So for now, the gravitational waveforms are implemented on RNNs, which is governed by these equations. The hidden state uh, acts as a memory for the recurrent updation of each and every discrete time step of a waveform, which is given from the HDF file. And yeah, so these are the two equations governing the updation of the memory and the output. And the training is our normal L2 square. And this is just a pictorial depiction of an RNN, how it works, the recurrence and how the memory is updated, and multiple outputs are given out. So each and every time step and each and every input is taken care of. I'll show the numerical results ahead. The second model is of a convolution neural network, primarily used for image processing, but here if model it into a one-dimensional formula, it does a good work in recognizing patterns, while RNN looks into a memory versus a temporal uh, data frame. CNNs work better in a pattern-based data frame. It is better in recognizing patterns. So this is a normal convolution, which we discrete convolution, and the training is same. And this is just a depiction on an image. I've got from the 20 waveforms which I was given. I took 14 of them for training, 3 for validation, and 3 for testing. Bodies, and I have done 4 modelings, RNN and CNN, and both of those models, one in time domain and another in Fourier domain. So sorry, in the frequency domain, I Fourier transformed the whole waveform, and I did the modeling on the Fourier domain, which was given after the Fourier transform, and these are the results. One could see the Fourier domain has a better output compared to the time domain in each of the cases. That's because in Fourier the frequency and the pattern recognition of some noisy data is smoothened out. So due to those smoothings, the prediction is comparatively better, and yeah, we could improve the results by taking more data. But for now, I was working on 20 data because it was a bit time taking, and I can take it more further. But I decided to go ahead and look into this physics informed neural networks. So basically, the idea of physics neural networks is quite simple and brilliant, if I must say, because the extra idea is there is a normal neural network and it gives us a prediction, but the additional part is the whatever governing physics PDE which we have, it will be taken into account and a loss, uh, a part of the loss will be given. So basically, the construction of a physics informed neural network is we have a underlying physics formula which could be a PDE and ODE. ODE works a bit better, but yeah, a PDE is a major thing which we want to solve. The initial neural network gives us a approximation answer. It tries to predict it, and then we compute the derivatives here. And after computing the derivatives, we take a residual error. So the error is basically our partial differential equation. It should be zero, but if it is not zero, that means we are deviating from a correct physical property. So that's the main idea of these additional loss. So the loss is just the data. There are some weights which we can assign. I'll show you how the weights gives us a different uh, output. So first is the data. Another beautiful thing of physics informed neural network is we can work with lesser data compared to the other neural networks, because other neural networks are highly data driven. They need data at each point which we are looking at, while in physics neural networks our physics defined loss function can help us in reducing the data. So the three losses are: one is the data driven loss, the other is the physics PD loss, and we can additionally put another loss of initial condition or boundary conditions. So a normal just these are just the definition of the losses. The data driven is just against the true value, and that's also in L2 norm square. And physics informed also, just to keep it positive, we keep square it out, so our loss is positive and doesn't give a wrong an addition and subtraction to zero. That's something which we don't aspire. So this is a simple physics informed neural network implementation. This is an underdamped system. I hope the dots are clear of the figure. So these red dots are okay. I'll first start with the blue line is the true solution, and the red dots are the data points which I took for training the artificial neural network and the physics informed neural network. So I wanted to predict want these neural nets to predict this underdamped oscillation till from 0 to 20th second of its oscillation, and the data points are limited till 5 seconds. So there were 50 data points, we can increase or decrease it, and the orange line here, this depicts a normal artificial neural network, and the green line here, I hope here till here it's a pretty good depiction of this is the physics informed neural network prediction. It wavers off a bit. That can be fixed with adding more hidden layers or increasing tuning the hyperparameters of the neural net. These are the hyperparameters of the artificial neural net, and the physics informed neural net is same. The only addition is the physics informed loss part. So this is just an implementation on one waveform, and like the initial 5 seconds and how it goes on. Then again, this is another implementation of a more generalized case. Like I took about 40 waveforms, and then an unknown test case was given, and the physics informed neural network was said to forecast it fully from 0 to 20th second, and this was just a random sampling, like 50 samples, but from 0 to 28th second. And in the first, the top upper plot, the weights for the losses are as given. Data is 1, physics is 2, and initial condition is 2. While in the bottom weights, it is data 1, physics is 4, and initial condition is 2. Due to the increase in weight for physics condition, this if you see this uh, line tries to predict it better. It's still not perfect. The epochs for training could be increased and uh, the prediction could go better. But for now, this is the plots which I felt should be given out. And just to summarize what I said, machine learning helps us to look into the waveforms and maybe can help us in decreasing the computational efforts. RNN and CNNs are, in general, neural nets are powerful data-driven rules, but when we are short in data, physics-informed neural networks can help us a lot. It also incorporates our the correctness of our physics equations. So that's it from my side. Thank you.
Thanks, sir. Yeah. So you can be here like maybe for
Yeah.
2 more minutes. You can come a bit
Yeah,
further.
okay.
Maybe focus. Yeah. So any questions? We'll happy to answer.
There are many ways we can go, like in gravitational waveform, which I am looking at now. One could be we take the full Einstein equation uh, formula and try to incorporate that. It will take more training. Another one could be another thing I was looking at, maybe just going at the solutions of the gravitational waves, the non-Newtonian inspiral equations. Uh, those could be used. That part, like as I said, I am a new joinee in this group, so
Yeah, that will not
Yeah.
be important for post merger.
yeah.
But yeah.
But incorporating, as far as I am concerned, the computation part shouldn't be difficult. The part of us selecting which equations which we want and what, how much importance do we want to give in the weights of the uh, data versus physics. Sorry, I went a bit too ahead. The weights of the data versus the physics laws. That is the user's choice, and in my opinion, implementation shouldn't be that difficult. The choice of what we take should be the more intuitive and more controllable part.
So the main concern is that we don't have any ODE which describes post-merger waveform, right? These are the results of the 3D evolution, and at what point far from the system we take the wild scalars and calculate the waveforms. Now the question is, what is that ODE which governs this? So we don't know, right? And if we can find it, then that will be amazing in its own way, because then we can just use that as a waveform. So yeah, we don't know. Thanks. Yeah, Anupita, yeah, please go ahead.
Hi, yeah, it's an interesting concept. Can you just maybe tell? I was curious about the plot that you showed, where you showed these, I think, orange or red points, which is your data. Yeah, these points. I was just curious about the irregular sampling of this curve, and how did you decide? And do you think there is going to be some optimal way to sample the same data, same number of points, but just distribute them differently, and that would achieve better results?
Yeah, I had just given a random seed of 42, a generalized case, and I just selected 50. So in my mind, I just wanted to take the most random thing. Yeah, a more uniform distribution could give us a better solution. For in my mind, I wanted it to be totally random. So that's why I didn't go into taking a uniform selection of data points. I just wanted it to be random. Yeah, a uniform data point is obviously better. We want to cover as much, like for another day I and Professor Rahul were discussing about sabermetrics. So we definitely want to, when we go into those higher dimensions and different equations. Luckily, this is just a simple underdamping equation, so such cases doesn't arise. But yeah, in this case, a random data selection was okay. It could be better from a more uniform data selection, definitely.
But model will be less general, right?
Yeah, it will be less general, but yeah, then if we uh, give our resources and time to selection data, which we'll have to give it in those higher dimension problems. In that case, there needs to be some uniformity in our selection so that we can cover as much as possible, or else our model will depict one side of the sabermetrics, while if we give a test case of another side, it will just give us a wrong answer. So yeah, data selection point is a bit of something which we look into, but here it was just a random selection.
Yeah.
Thank you.
Hi.
Yes.
Thanks for a nice talk. I just wanted to like have one suggestion and one comment, like question. So the question is like for the physics informed part, can we have not focusing on the ordinary differential equation, but focusing on, for example, universal relations, right? Like Boswin et al. People, they have come up with these empirical relation for peak frequencies and different frequencies. So we can use those like outputs and then compute those frequencies and then impose those frequencies in your output. That's number one. How feasible is that? Is it something needs that can be pursued, or
So there, my view is that you will get what you put, right? So if I put a specific relation between peak frequency and some input parameter, which is some kind of approximation of the real NR data, right? So then we are training our data on assuming that, but that's itself is an approximation. And suppose if you want to check it, whether that relation is satisfied in real world, then you will not be able to do.
right.
So my view is that if we are doing machine learning methods, then we should do directly on the NR data and also incorporate uncertainty in the
Yeah.
NR data somehow. That will be the correct thing to do. But
Okay.
any other model, we can train on any model, but
Right.
other models will be uh, not general enough.
Okay.
But for data analysis aspect, like detection aspect, one can probably do that.
Okay.
I mean,
Thanks.
there is no issue in doing that. I am not certain how good the model will be, but any model should, like, the idea of machine learning is you give it anything and it should try to learn it in an analytical and numerical manner. So it is feasible, but I'm not sure how well the prediction could go.
Okay. Thanks. Just one suggestion: you should also explore the architectural design. So of the neural network. So given a particular architectural design, you can actually gain or lose on the like errors and stuff like that. So just
Okay.
yeah.
So what is change you suggested?
So the Bayesian optimization is there for arc. So
General, like layers of neurons and
yes,
Yeah.
So that is actually needed to finalize the architecture. So that's kind of one of the important steps. So just a suggestion.
Okay. Thanks a lot.
Thank you.